American bombing of Nagasaki during World War II. A power plant that provides energy for millions of people. A car from Back to the Future that allowed time travel to be possible. What could all of these three things have in common with each other? Well, the answer is pretty plain simple. Plutonium. Yeah, that's right. This green glow-stick looking thing in front of you is plutonium. But what could something so innocent looking like plutonium really do? Well, first, it could lead to pretty sights like this. Plutonium is pretty powerful and can light up large cities and other things that require a lot of power. But it can also do this. Pretty scary, right? Yeah, that's what I thought. So then, how could something that looks like a glow stick do so much good, but so much bad? Well, we'll just have to wait and find out by the end of this video. Plutonium, with chemical symbol Pu, is any atom that contains exactly 94 protons. Since it comes after uranium and neptunium on the periodic table, people thought it was appropriate to name it after the next planet in line, Pluto, even though Pluto is sadly not considered a planet anymore. As mentioned before, plutonium is located near uranium and neptunium on the periodic table, which are all actinides, since the electron shell that is being filled for these elements is the 5s shell. Since it's an actinide, plutonium is a metal, and a very radioactive metal to say the least. In fact, it's so radioactive, if left to rest by itself, it will slowly start to glow due to how much heat it produces from its radioactivity. But what exactly is radioactivity? I'll let this video coming up to explain it for me.
And just like when an atom gains or loses or shares electrons to stabilize its outer shell, when the numbers of protons and neutrons aren't ideal, the nucleus releases some of them to try to reach a stable configuration. When a nucleus decomposes in this way to form a different nucleus, that's radioactive decay. Let's take a look at what may be the most famous radioactive element, uranium. By far the most common naturally occurring form of uranium is the isotope uranium-238. More than 99% of the natural uranium in the world is in this form. U-238 spontaneously decays into thorium-234 in a process that releases something called an alpha particle. This is called alpha decay, and the particle that it emits is basically the same as a helium nucleus, 2 protons and 2 neutrons. We even describe it that way when writing it. The second type of radioactive decay is beta decay, which simply emits electrons. It has somewhat higher energy than alpha radiation, but it can still be stopped by a sheet of aluminum foil or even the top layers of your skin.
Alright, so hopefully after watching that video, you have a somewhat decent understanding of what plutonium is and how it acts in a basic environment. But on to the next question. How exactly does one get their hands on plutonium? Well, almost all of the plutonium in the world is formed through this method right here. First, the story starts off with a happy little uranium-238 atom frolicking through the world, and then, bam, a neutron hits it so hard that it joins the atom and turns it into uranium-239. Well, uranium-239 is pretty unhappy and pretty unstable by itself, and in less than an hour, it completes beta decay to turn into neptunium-239. Although neptunium-239 is more stable and happier than uranium-239, it's still pretty sad, and after around 3 days, the new atom again finishes another cycle of beta decay to turn into, you guessed it, a much happier and stable plutonium-239. Because of how intricate this process is though, it is very uncommon to see it occurring in nature, although not impossible, and is also the main reason why most of the plutonium in the world today is man-made. The first creation of plutonium happened on February 23, 1941, at the University of California, Berkeley, by a group of people using a very primitive particle accelerator called a cyclotron, which is being shown up on the screen right now. However, the first large boom of plutonium development for actual experimental use occurred during World War II during the United States Secret Manhattan Project, which is the codename for the project that developed the first atomic bomb. Scientists in this project were hoping to find an effective method of creating an alternate for uranium that could deliver more explosive power as well, and they struck gold. These scientists found out that if you can take a chunk of plutonium and squeeze it really hard, it implodes on itself and starts off a massive chain reaction of nuclear processes that eventually leads to a massive explosion. This style of bomb was the same type as the Fat Man bomb, which was the bomb that the United States dropped on Nagasaki, Japan at the end of World War II. Additionally, as it can be seen through this summary of a 1995 research paper, atomic bombs need much less plutonium than uranium to achieve similar amounts of stopping power. Specifically, to create a low-tech atomic bomb that is equivalent to 20,000 tons of typical explosives, you would need 16 kilograms of 90% enriched uranium-235, as compared to a smaller 6 kilograms of plutonium-239. Plutonium additionally also has another well-known use, the generation of electricity. This can be done through one of two manners, by taking advantage of its fissibility or by taking advantage of its radioactivity. Fissibility, or the ability for an atom to undergo nuclear fission, is most commonly associated with the use of nuclear reactors. On your screen right now is the Breezale nuclear reactor, Penn State's official fully functioning nuclear reactor with plutonium-using capabilities. But how exactly does a facility like this use an atom like plutonium to create so much energy? Take it away, video.
So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway.
So now you know about plutonium in nuclear reactors, but what about plutonium in space? Yeah, that's right, space. Like planets and rocket ships and the whole 9 yards. Another method that plutonium can generate electricity through is by taking advantage of its radioactivity. Remember how I said plutonium generates so much heat because of its radioactivity? Well, the device being shown on your screen right now, called a radioisotope thermoelectric generator, or an RTG for short, can convert this heat into electricity. This type of energy generation is mostly used for long-term energy goals, such as energy required for long-term space travel. Almost all of NASA's recent space missions have utilized a plutonium-based RTG to generate all of its onboard electricity. The RTG is most probably known through its appearance in The Martian, in which Mark Watney uses it as a heating device to help him endure the long, cold nights on desolate Mars. So, for the last part of this video, I'll be briefly talking about why plutonium is much better than uranium. First off, plutonium is much more powerful than uranium in most of its practical uses. It can generate much more electricity per kilogram in a nuclear reactor and much more explosive power per kilogram in a nuclear bomb due to its producing more neutrons on average than uranium in nuclear fission. Additionally, because plutonium is so much more radioactive than uranium, it can be used as an effective source for long-term energy generation, in which uranium can barely be used for.